Welcome back. So we're moving on with our elasticity lecture. So I want to hit how do we represent our tensorial elasticity equations in terms of matrices. So we know how to write second order tensors as matrices. Here we're looking at how do we write a matrix equation that captures a fourth order tensor acting on a second order tensor. There's some subtleties here. The first being that when we talk about second order tensors, the matrices that represent a second order tensor also transform in the same way that a second order tensor transforms. Right? So we can write our transformation equations as if A is a second order tensor, A equals Q, A prime, or transformed A prime equals QA, Q transform. I have a matrix way of writing that transformation. That's not true for fourth order tensors. So I can write a matrix that represents a fourth order tensor, but that matrix does not transform. We have to always think about transformation relationships with respect to the full fourth order formulation. But what we can do is we can write our stress as a vector and our strain as a vector. And there's some subtleties about how we have to do that. We can't just string them out. But we have 6 components of stress and 6 components of strain, right? Not counting the symmetry, right? 3 by 3 is 9 by 9. But we know that 1, 3, and 3, 1 are symmetric. 1, 2, and 2, 1 are symmetric. And 2, 3, and 3, 2 are equal. So we only need to consider 6 of our stress and strain terms. We can write our stiffness matrix as a 6, or stiffness tensor as a 6 by 6 matrix. And think about the matrix vector product that we can use to relate stress and strain. So we write this as a stress vector, a strain vector, and a stiffness matrix. Sigma m equals c mn epsilon n. Can also invert it and think about what our compliance matrix needs to look like. We also write this in such a way that our stiffness matrix and our compliance matrix are symmetric, and we also want it so that our stiffness matrix is the inverse of our compliance matrix, so that I can invert this 6 by 6 matrix to find the components. So these requirements, that we want them to be symmetric and that we want our stiffness and compliance to be related by inverses, means that we're going to have to write our strain vector in a different way than we write our stress vector. And you'll see what I mean in a minute. Okay, so to go from our full, here's our 3 by 3 stress tensor, and we write it out. We just go down the diagonal, sigma 1, 1, sigma 2, 2, sigma 3, 3. Then we go back up around. So we go this, 2, 2, 2, 2. So it's sigma 1, 1 equals sigma 1, sigma 2, 2 equals sigma 2, sigma 3, 3 equals sigma 3, sigma 2, 3 equals sigma 4, sigma 1, 3 goes to sigma 5, sigma 1, 2, there's a typo there, dang it, is sigma 6. Okay. Strain, we have to put a half in. Right? So some authors use gamma down here to denote the shear strain terms in the strain vector, so they don't need to worry about this 2. but I like to keep it all in terms of the tensor. Right, so it's the same pattern down the diagonal and then counterclockwise or anti-clockwise around. But you have to remember to put the 2 in there for your shear strain terms. And again, that 2 is required so that we have a symmetric stress or stiffness and compliance tensor, and that we can keep our inverses related to each other. The stiffness is very straightforward, just like the stress. So we just compress the indices ij to m and kl to n. So 1, 1, 1, 1 would C1, 1, 1, 1 goes to C1, 1. C1, 1, 2, 2 goes to C1, 2. C1, 1, 3, 3 goes to C1, 3. C2, 3, 2, 3 goes to C4, 4. Right? Very straightforward. For compliance, we have scaling factors, just like the strain. And if m and n is not equal to 4, 5, 6, then it behaves just like stress. We don't have any scaling factors. If m and n is, or n is 4, 5, and 6, if one of them, then we need a factor of 2 out front. So Sm becomes 2 Sijkl. So S14 is equal to 2 S1123. If m and n are both 4, 5, and 6, then we need a 4 out front. So Smn in that case is 4 Sijkl. So the example is S5, 4. 5 is 1, 3. 4 is 2, 3. So S5, 4 is equal to 4 S1, 3, 2, 3. And these, again, these scaling factors are in there for a couple different things, right? So we want to ensure that stiffness and compliance are related by inverses. We want to ensure that they are symmetric. And we want to ensure, another factor is we want to make sure that our strain energy density is 1/2, or that this dot product, right, sigma ij epsilon ij is the same as sigma m epsilon m. Right? So the multiplicity of the shear terms, or the shear strain terms, is accounted for. Okay. So for isotropic stiffness and compliance matrix, right, C11 is equal to 2 times our shear modulus plus our lambda, the Lemay coefficient. And for the stiffness, it's 1 over the Poisson's ratio. Right? So we typically write our stiffness matrix with respect to the Lemay coefficients for isotropic materials, and we write our compliance matrix with respect to Poisson's ratio, shear modulus, and Young's modulus. These are just kind of the standard ways of writing it, so that's the easy to remember, and you don't have complicated terms up here. Of course, we can always write our stiffness with respect to Young's modulus and Poisson's ratio as well. These happen to be the forms that most books put forth because they're the most straightforward. So that is the how we represent the stress and strain elasticity equations in matrix form. And we have one last little part where we'll go over the forms of the stiffness and compliance matrices for anisotropic crystals.